This question is from GATE 2015, Mechanical Engineering paper, Set 1, question number 38. Considering massless rigid rod and small oscillations, the natural frequency in radian per second of vibration of the system shown in the figure is. So if we assume that there is a clockwise rotation here due to the weight of this mass, we will see that the rod will have a deflection like this, right? Because this is a rigid rod, it will just rotate, it will not deflect. Consider angle of rotation theta, small angle theta. So theta is nothing but our generalized coordinate in this vibration system. We need to first find out the equation of motion to find natural frequency, because natural frequency can be found out using under root k star by m star. This is the value of natural frequency specifically for generalized coordinate system, that is theta. So we'll have to find out the equation of motion first. For equation of motion, for that we will find the Lagrangian L as kinetic energy of the system minus potential energy of the system. The entity that is responsible for kinetic energy is the mass that will move. So kinetic energy is equal to, mass is in a circular motion here. So we will take the rotational kinetic energy instead of the linear kinetic energy because of the rotational motion been happening. We have kinetic energy as half into mass moment of inertia of the mass I into omega square. This omega is the angular velocity of the rod. It's not the natural frequency of the system. This is different. Now spring doesn't have any kinetic energy, it will have the potential energy. So total kinetic energy is half I omega square plus 0. Let's write I value and see what is the kinetic energy. So we have half into I is, no details of the dimensions of mass are given. So we will take point mass and calculates its mass moment of inertia about this hinge point. Let this hinge point be O. About this hinge point, mass moment of inertia of mass is m into the distance square. So we have m into 2r whole square into omega square. Omega square can be written as theta dot whole square. After simplifying, this comes out to be 2m r square theta dot square. Similarly, we can find out potential energy of the system. Potential energy is possessed by spring, not mass. So potential energy is given by half into stiffness of spring K into its deflection square. So this deflection of the spring or the compression of the spring will be giving us the value of x. Because theta is small, we can write x as r theta. So let's substitute that. We have half into k into r theta whole square. So this becomes k r square theta square by 2. Let's find out the Lagrangian now. We have the Lagrangian 2 mr square theta dot square minus k r square theta square by 2. Now we can find out the equation of motion by using d by dt of partial differential of Lagrangian with respect to theta dot minus partial differential of Lagrangian with respect to theta is equal to 0. This is nothing but the equation of motion. After putting L value, we will get the specific equation of motion for this particular system. So let's put L. By differentiating first with respect to theta dot, we get 4 mr square theta dot. And then when we differentiate it with respect to time, we will get 4 mr square theta double dot minus differential of potential energy with respect to theta will give us minus 2 kr square into theta by 2 is equal to 0. So we get the differential equation 4 mr square theta double dot plus kr square theta equal to 0. Now we have our m star and k star values. So we can find the natural frequency as omega n equal to root over k star is kr square and m star is 4 mr square. R square by r square gives 1. Omega n is equal to under root of k value is 400 divided by m is 1. So we can substitute 4 into 1. We have 4. Let's go back and see what the answer is. Answer is option D, root over 400 by 4. We don't have to simplify. The option given itself contains under root 400 by 4. For more information on generalized single degree of freedom systems, you can refer to the NPTEL video, Module 1, Lecture 17, Generalized Single Degree of Freedom Systems, Equations of Motion, from the course Structural Dynamics by Dr. P. Banerjee. He is from Department of Civil Engineering, IIT Bombay. I hope this solution will help you clear your doubt. Thank you.